All right. Why don't we get started? So we're probably going to end early today. I got roped into a university division business-related meeting, which is going to cut into some of my other time. So we're probably, or I'm planning to finish earlier today, and not go the full class period. So where we left off, well, make sure again, as always, that you're keeping up with the reading. It's really important excuse me, to engage the material through the book, in addition through to, of course, attending lectures in class and screencasts if you need to. All right. So where we left off, we talked about the pthreads example in Linux at the command line, in Ubuntu in C. And in this program, we defined a function called runner, and it had a specific function signature. It returned a pointer to void, so it had a void star as the return type, and it also had a void star as the parameter. And that was intended to be general, and that is going to be the style, if you will, of the function or task or behavior that's going to be executed when you create a thread. And so we did a little bit of bookkeeping to check for the command line, and then the business end, if you will, of this program. We initialized the thread attributes, and then we did pthread create. And this pthread create was given a number of things. It was given a pointer or the address of the thread ID and the attributes. And that's because when you call pthread create, it's going to instantiate the thread, but it needs some place to store the information about that thread, the identifier, which is stored in that variable TID. So that's why you give it the address of TID to make it a pointer, a memory location, and then also the attributes, so you know a little bit about some of the default behaviors of this particular thread. Okay, and so once pthread create is called, that runner function, and that's another parameter, it needs to know what task or what function to execute in this thread. Runner goes ahead and executes, and once runner exits, it calls prior to that pthread exit. And that pthread exit is this signal between the thread and the caller of pthread create that created it to let it know that the thread is done. And so, akin to how a parent process, waits for the child process, the thread that created the child thread, as it were, also evokes this join, which or calls this join, which is in essence waiting for that thread to exit. Okay. All right. Now, in the example we gave, we only created one thread, but the beauty of threads, as we talked about, when you parallelize the behaviors of your program, you can essentially compartmentalize it into a number of functions or tasks that that program can take, and then those tasks that can be performed either concurrently or in parallel, you would call them in threads. So you can imagine then, instead of just having a single pthread create, you could call pthread create some number of times, one for some number of tasks into which you've divided your program. Okay. Any questions about this? Make sense? Okay. So we have 4 weeks left after this week in the semester. Not a lot of time. And what my plan is, in probably about maybe 2 weeks or so, have another exam, and then um, also distribute a semester project that'll tie together a lot of this stuff that we've been talking about. I still haven't decided if it's going to be in Java or in C. That is to be determined. I should know, hopefully, by beginning of next week, what the structure of that final project is going to be. So the final project will be your final exam, and it'll have some moving parts, so to speak, to give you some exposure to some important concepts, namely threads, maybe shared memory, and synchronization. And you'll get experience with is how the design of a program that makes use of these operating system facilities can give you a much higher performance program. I just have to figure out something that's not too heavyweight, whether it's streaming or maybe a simple web server or what have you. Okay, all right. So we can call pthread join more than once to have some number of threads. And of course, if you call pthread join pthread create more than once, you also need to now wait for those threads to resolve or to exit. And so for that multiple call for pthread join, essentially, when you create those threads, the pthread create, you'd create an array of pthread IDs, and then you'd call pthread create some number of times, maybe in a loop, and then for each thread that you create, you'd store its thread ID, which is of type pthread t, in one of the positions of this array. Now, in the book, the name of the array, they just happen to call it workers. And in essence, a worker is nothing more than a thread that performs some task. And so the join for this and waiting for the threads, you then loop through your workers array and you call the join on each one so that you get the exit status for each of those threads, you being some process or parent thread that created all those other worker threads. Any questions about this? Make sense? Okay, so it's just joining in a loop to iterate over all those threads that were created. And so the dual of this would have been the pthread create in a loop, storing each one of these thread IDs in a position in the workers array. Okay, so let's talk about Java, and we'll segue out to Ubuntu and show you a Java example. And Java supports threading, and we'll cover the Java version of doing threading, but only for the simple threads. And I'll leave it to you when we talk about thread pools to go off to the Java doc. There are tons and tons of examples of thread pools, but I'll explain what thread pools are after explaining what simple straight Java threads are and why thread pools are important, more importantly. So Java threads are part of the Java runtime, and in the Java package system in java.lang, right, which is where all of the basic language elements exist, all the language classes. And so java.lang.thread is the class that's used for implementing threading in Java. Now, of course, as an object-oriented language, there are a lot of facilities that are in place to make it easier for you to create and manage threads. And so what you'll see in the API, the threading class, the thread class, has a join method. And when you want to wait for a thread, you just call join on that reference, and you don't have to track all of these thread IDs. So it makes things a little bit easier. So this Java thread, when you create it, it can be created by two different approaches. One is to either implement the runnable interface or to extend a Java lang threads. And so you can create a Java thread by making your thread a subclass of Java lang thread, or if you implement the runnable interface, you have to satisfy all the methods imposed by the runnable Java interface. And then when you instantiate your runnable class, you instantiate it and give it to the constructor of an instance of the Java lang thread object. Okay, and so you're going to need Java lang thread, and whether you choose to use the approach of giving its constructor runnable, or if you extend Java lang thread to implement your threading, one of those two methods, are how you implement Java threads. And so if we were to look at the Java doc, and well, maybe I'll do that a little bit later. I'll first go over some code. Um, so let's take a look at some code, right? So this is an example, and I've pre-written it at the command line so that we kind of save a little bit of time because I have that meeting. That kind of cuts right after this class. But there are a couple of things going on here. And this example is effectively a repeat of the pthreads example in C. And to jar your memory, in that example, you created a thread and you gave it an integer, and it ran in a tight loop, and in that loop it iterated, adding all the numbers up to including that integer. So if you gave it a 3, it would add 1, 2, and 3 for a sum of 6. Okay, so this is a repeat of that, but it's implemented using Java isms, if you will, for use of its thread APIs. And so here they create a sum class, and that's going to be sort of an encapsulation, a wrapper object to hold the value of sum. And you might be asking, well, why don't they just use an integer? Why use a whole class? Because you want to make use of the type system in Java, and that becomes especially important if you're going to be sending things back and forth across the wire in a distributed system. So here, this sum has, in object-oriented parlance, something called an accessor and something called a mutator, right? An accessor as the name implies, is a method that gets some value from the object, a getter, as it's sometimes called. And then the mutator is something that changes the state or the value of some instance variable in an object. And so we have the accessor get sum is going to return the sum, which is a private instance variable inside of the sum class. And then we also have the mutator set sum, which is going to change the value of this private instance variable sum in this sum with a capital S object instance. Okay. Any questions about that? Does that make sense? Okay. And so now that's the basic data, if you will, for which our application, our threaded application or example is going to traffic. It's going to traffic in these sums. And so now we have our runnable. And so the approach for implementing threads in this example is to create an object that implements a class rather that implements the runnable interface to satisfy those methods required by the runnable interface, which is just to have a run method implemented, and then to now instantiate this and give it to the constructor of a thread instance. So here we have the summation class, so it implements runnable. And so when you see interfaces in Java, the purpose of interfaces for Java was to solve the multiple inheritance problem. If you've ever programmed in C++, you can have multiple inheritance. You can have one derived class implement two or more other classes. And so what this multiple inheritance means is that you can have more than one set of methods as defined by an interface that an object uh, implements, but you can group them together as named types, and you can have more than one. So you could have runnable, and let's say you had some database interface, and it was called queryable. You could also implement queryable, both of those sets of interfaces in this class that we're calling summation. So that's the purpose of having interfaces, is to solve the multiple or implement the multiple inheritance construct in object-oriented programming. But nonetheless, we have class summation. It implements the runnable interface, and as an implementer of the runnable interface, it's required to have a definition for a run method, and specifically that run method must be public and have void return type and have no arguments. So here inside of our summation class, we have the implementation of public void run with no parameters, open, close, curly brace, and within that block, it takes the sum, which starts out and it iterates up through upper from 0 to upper, and it adds each of those values. Now upper is the value that is given. Ultimately it comes from the command line interface when you run this Java program. And so our summation class is instantiated into an object with two pieces of information. One is the integer that tells it how many terms to sum together in the loop, and then the other is ultimately the result of that sum. So what you'll see here when we instantiate a summation class or object, we get upper is our in our constructor, and then we also have an instance or reference to a sum type, where sum is defined above. So the whole purpose of sum is just to store the resulting value. And in the implementation of the run method, once we're done iterating through that loop, summing together all those terms from 0 up through upper, that integer, we then call set sum, the mutator, on this sum instance, which had been passed in through the constructor. Okay. Any questions about this? Does that make sense? All right. So this is our runnable, and this defines the behavior or activity to be taken when the thread is executing. And this is akin to defining that runner function in C, right? This is the function that's going to be executed. So let's lastly take a look at the driver, right? And the driver is going to tie all of this together. This is where you perform Java's equivalent of saying pthread create, right? And doing the pthread join. This is the actual invocation of that behavior, but the behavior is defined by the summation runnable instance. Okay, so we do a little bit of bookkeeping inside the main method, and we check to make sure we have the right number of arguments and do some error checking, and I won't go over that. But the business end of this, here we instantiate the sum object, and that's going to hold the result of performing the summation. And then we're going to parse the argument to get that upper. Remember, this is going to be specified on the command line. And then we create a new thread. And so when we create a new thread in the constructor, we give it an instance of a summation. So that's the behavior. The thread is the execution context, but the specific behavior to be executed is going to be this summation instance. And so the summation instance, we give it the upper, which was obtained through parsing the command line, and then we give it a reference to a sum object, which is how it communicates its result to the outside world. Okay. All right. Any questions about this? Make sense? All right. So we call now on this thread reference, we call the start method. And once you call the start method, that's when the thread is executable. And now it can execute that run method. It gets called inside of that summation instance. Okay. So now in this try block, after the thread start is called, now this summation is running, right? That behavior is running, and it does its thing. And the interesting part about the Java case is that um, you don't have any thread exit here. Once this run method completes and it goes out of scope, right, the thread is done and the Java runtime handles all of that stuff for you. And so you notice in Java, you don't have to call thread exit or any sort of give any sort of notification that the thread is done. So you call thread start, it runs, and then run completes. And now using that thread reference, the same one you use to call start, you issue the thread join, right? And that's waiting for the thread's exit status for the thread to complete. And you'll note here that all you needed was the reference to the thread. You didn't need any notion of a thread ID to manage which thread, because indirectly through the reference to that thread object, the Java runtime handled all of that for you. Okay. All right. Any questions about this? Make sense? Okay, so let's try this out in Ubuntu. And I've sort of pre-written these pieces, and we can just go over again uh, some of the key parts of each of these parts of the program. Okay, so let me bring up Ubuntu, VirtualBox, I mean, and we will run the virtual machine instance. Take Ubuntu. And so while that's loading, let me show you the Java doc for Java lang thread. And as you can see, it tells you how you can use thread. So here's an example. You can create this thing. It says here's prime thread, and prime thread extends Java lang thread. And in that case, when you extend it, you can override its run method, and that provides the execution that this thread will perform. So then you create an instance of your prime thread, which extends Java lang thread, and call the start method. Right, that's one way implementing threads. And then the way we just discussed for the example code, which is also in the book, is you create a runnable instance, and then you create a new thread, and you pass that runnable instance to the constructor of the Java lang thread. So there are two different ways. Which one is better? It all depends on what you're after. If you have a number of different tasks that you want to switch off on, it might be better to go the approach of using runnable. Some people just prefer to have extensions of Java lang thread. So it really, honestly, doesn't matter. It's just a matter of taste. Okay. All right. So let's look at where our virtual machine is. It should be up there. It is. So let's log in, OSC, and bring up a terminal and take a look. OSC, and we'll bring up a terminal and take a look at these Java classes that I've written ahead of time. Make that a little bit bigger. Okay, so let me go into the Gary Holness directory where I've been putting all the code. Start at Java. Okay, so we have sum, we have summation, and we have driver. So if I take a look at sum.java, just as we had in the printout, it is just a wrapper class to encapsulate that sum integer. It has an accessor, get sum, and a mutator, set sum. Okay, so that's not very interesting, but more interesting is summation. So let's look at summation. So we look at summation, and so this is our runnable. So we implement class summation implements runnable interface and therefore is required to provide a definition for the public void run method. And so we have two instance variables in this. They're both private in scope. The upper, which is the upper bound that this loop is going to iterate over in summing terms, and then some value, which is a reference to a sum object, a wrapper class that has the accessor and mutator to encapsulate the result of summing. And so in our run method, of course, we loop. Each iteration we're summing loop index to sum, and then we use our sum, the mutator on our sum wrapper class, and set that sum. Okay, so this is passed in both upper and that wrapper are passed into the through the constructor. All right, so let's take a look at driver. And again, just as we had said before, driver is the thing that kind of kicks all this off. We have our main method. We check to make sure we have the right number of arguments at the command line. And then we will see what the value is to see if it's a value that's greater than 0. It, in this example, only sums things that are natural numbers. And we instantiate a sum object, a wrapper. We parse that argument and convert it to an actual integer type. And then we instantiate a summation, giving it that upper bound integer and the reference to sum object. And then we use that summation object instance in the constructor of that thread. And the reason why we can do that is because it is a runnable. It implements the runnable interface. So then we call thread start. And then once we call thread start, the thread starts executing. So we'll be executing the run method of that runnable in summation, and then we call thread join and try catch block to try to catch any errors that might happen, and then we exit. Okay. Any questions about this? Make sense? And so threading gets interesting when you have lots of threads doing lots of things, which we will get experience with, certainly in the final project. Okay, so let me compile this. And I'm not going to do the makefile this time. Java C -D dot. So that means when you're compiling, look to the current directory for class files, and then -cp dot. That -cp stands for class path. If you're looking for libraries of objects, include the current directory on your class path, and I'm going to compile star.java, all the Java files in the current directory. Now, certainly, there's nothing wrong with using an IDE like NetBeans or Eclipse or some other such thing to write Java, but for the sake of demonstration, I'm just going to do it from the command line. So I do that compilation, I don't get any errors. So let me now run it. Java dash class path current, and I'm going to run driver. Now, if I run driver and I don't give it anything on the command line, certainly that's an error because it's expecting to see an integer parameter specified for driver class instance. And you'll notice it outputs that error message. Likewise, if I gave driver a negative number, like -1, right? It must be greater than or equal to 0. So that bookkeeping and error checking in the main method of driver.java is certainly working. So let me now give it a 3. And when I do that, of course, it takes that 3, it parses it, converts it to an integer called upper, and then it specifies that upper into the constructor along with the sum object reference to that summation. And it takes that summation, puts it into the constructor of a Java lang thread, because it is a runnable interface that it implements, and then it calls thread start. Okay, so let's take a look at that. All right, the sum of 3 is 1 plus 2 plus 3 is equal to 6, so it is running. Now, in your careers, when if you're choosing to work in industry, you have to kind of make a choice about which side of the world you live on in terms of writing software for in software development. There's the so-called front end, which are those parts of the software that interface with users and people. And there's so-called backend, which is the part that does computations and queries and all sorts of stuff like that, models and things like that. And so oftentimes the dichotomy is that you make a choice. Are you going to do front end or back end? The back end is all the server type applications, and it's never as interesting when you see it run. because you're focusing on things like algorithms and efficiencies and all sorts of stuff like that. And on the front end, you're dealing with graphical user interfaces and buttons and stuff like that. But you can also on the front end deal with other types of interfaces like joystick controls, virtual reality, other types of interfaces, touch screens, and other future devices that are out there. And so just be aware when you're on the job search, you kind of have to decide which side of the world you want to be on if you choose to go into software development. Okay. All right. Any questions about this? So again, it's not very interesting to say, oh, all that and all we see is one line of text. The sum of three is six, right? Oh, okay, that's back end for you, right? In back end, all you see is just the stuff that gets printed out. It's not as visually pleasing when you're doing back end work versus front end. Okay. Any questions? No questions? Okay. So let's continue on, and that's Java threads. And probably going to turn on the light for this section of the room because I'm going to write on the board uh, with a bunch of stuff as it pertains to a concept called thread pools. Okay, so implicit threading. Okay, so threads have grown in popularity, especially as processors have increased when you started going from single core to multiple core, right? And when you go to multiple cores, certainly you can take advantage of parallelism, and a very easy way from a programmatic standpoint to parallelize your application is to divide your application up into tasks encapsulated as functions, and then to have each one of those functions run by a thread. And so, as parallelism becomes more popular, threading became more popular, and as the number of threads into which a program's behavior is chopped up, as the number of threads increases, also the complexity of writing programs gets more and more difficult. And so, oftentimes, when something gains popularity and gets more difficult, the support for them tends to get offloaded into libraries as well, or facilities or assistance by the compiler to make it easier to write them. And so this has happened with threading in the form of something called thread pools. Now, I remember when I first graduated from undergrad and I started working in industry and research and development, and you had to do threading yourself, right? So this idea of thread pools, I'll explain sort of what the rationale is, and just more so show you what the API looks like. And so we'll look at this idea of the support offered by thread pools, and it's a way of defining a large group, potentially large group of threads, and there are reasons why you want to do that that are bounded, and makes it easier for you as a programmer to write applications that take advantage of it. Okay, and so this is one example of support by the library, specifically language libraries, for this idea of threading, since it is so popular. And so the advantages, why do you have a thread pool? Now, sometimes in some applications, let's consider things like a web server. Now, with a web server, so turn on that side, nope, that side, all right. With a web server, if you consider what happens, you have your web server here, your server, right? And then you have some client one. And of course, they're connected over the internet somehow. It doesn't really matter how they are. But you're going to have more than one client. And let's say you have n many clients. Now, n could be thousands, n could be millions, and in so-called internet scale is typically hundreds of thousands to millions, right? And so you'd imagine all these clients sending a request to a server, and it doesn't matter what that server is. It could be something like Netflix. It's a request to start a stream connection for the video server in the data center, or it could be a request for getting content corresponding to some item you're searching for on Amazon. So let's blow up this server and let's think about what happens inside the server when a request arrives. So we talked about our network communication when you're trying to communicate between two processes that are on different machines. And so you use a socket, and the socket accepts an incoming request, and that request is basically a piece of information, and it's coded. And in this case of HTML, you're going to say retrieve or get something, get some HTML file. And so you have a method or a name get, right? And you have the name of an HTML file also. And so that server takes that incoming request, let's call it a request, and that request has some information that's meaningful for a particular aspect of the program, right? Now, if you've taken computer networking, okay, you already understand this, but this is operating systems, and there's no assumption that you've taken networking. So this request comes in, but guess what? There's more than one request coming in from a client. So client one might issue request R1, client two issues request R2, and so forth, R sub n. So you have a large number of requests that are coming in. So if you have a large number of requests coming in, you need some way to handle these requests so that everyone has the illusion, if you will, that this server, this box, is responsive to whatever it is each of these clients wants, right? So what typically happens, you can think of these requests as some piece of work. So imagine, you're, a banker or what have you, and you're processing mortgage applications. Someone comes up and they put down a mortgage application in front of you. You process that, you look up something, you do some work, and then you're finished and you give back the result, right? Now, of course, if you had a lot of mortgage applications coming in, maybe you'd have more than one loan processing officer, right? You have a bunch of workers that are performing some task. So let's assume that these incoming requests, we have this notion of this basket of incoming requests and this idea of having a set of workers. They're going to take these jobs, if you will, from this basket of incoming requests, perform that work that it needs to process them, and then spit out the result. And that's exactly what a thread pool implements, this idea of having a set of workers, a pool of threads. And so typically what happens in a high performance server application, you have a queue, and this queue is associated with a thread. And when I write a thread, I'm going to have this kind of curly looking arrow here, right? That's how I learned it. I really can't stand this wiggled line. I think it's kind of silly, but that's what the book does. So you have a thread, and that thread's responsibility is to take incoming requests and put them on a queue. So you have that incoming thread, so let's call that T1. And anytime an incoming request comes in, it takes that request and it puts it on the queue. So it puts it at the head of the queue, right? So that's the head. Sorry, the tail of the queue, and this is the tail. So request R1 is put on the queue, then followed by R2, dot, 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 by R sub n. So you have the incoming requests, and they're handled, accepted by this thread, and all this thread does is take an incoming request and add it to the queue. Now, of course, if you had a high volume of incoming requests, well, you don't have to have just a single thread doing that. You can have another thread doing that and another thread doing that. So let's say you have T1, T2, thread T3, all taking incoming requests, and the only job they have is to take the incoming request and put it on to the tail of the queue, right? Now, of course, if their job is very, very simple, with simple things, you can make them, excuse me, very, very fast. And so you'd have a while loop in these threads, and these threads, all they do is look at the socket, or more correctly, the file descriptor. If there's incoming data, pull that incoming data, put it on the queue, and look back again, and keep doing that again and again and again. They're highly specialized, so you can do this very fast. So very quickly, you can take requests and add them to the queue. Now, of course, if you do that quickly, if you have a high volume of requests coming in from clients across the internet, this queue is going to fill up very rapidly. So now you have another set of threads, let's say T4, right? And this thread's job is to take a request off the queue, right? Process it and do the work associated with that request. Now, of course, if this is an incoming request from somebody across the internet, one of the pieces of information in this request R1 is going to be the address associated with the first client, the address associated with the second client. So now you have this thread, and this thread says, okay, my job is going to be to do the work associated with each one of these requests that's been accumulating in this queue. So these so-called worker threads can be general, and they understand all the different types of work that can be encoded in each of these requests. So now, if you can have one unit of worker, you can replicate that and have another one, and have another one, and have another one, and have another one, and so forth. But there's a caveat, right? This server is running some operating system. And as we said throughout the course of the semester, operating systems have finite resources. So one of the problems is, okay, well, let's say you had a million clients. You certainly don't have a million threads. No operating system does, right? At least not now. Maybe 20 years from now, I don't know. But the problem is now, as your load increases with the number of requests, certainly this queue grows. And the consequence of that is you're going to need more memory from your heap in order to accumulate more requests. You need more threads among your set of workers to handle all these requests, because if the queue grows unbounded, then certainly something's going to break, right? Now, if you're Netflix and somebody goes to netflix.com and you try to stream a video, what the customer sees is, I can't watch my video, or my video broke. And you don't blame the server load. Netflix is popular. You blame Netflix. Say, this stinks. I'm going to go somewhere else and use someone else's streaming service. So it's really important to have what's called graceful degradation. As you scale your load incoming on the internet side, right, the consequence is, of course, this is very fast, right, because they're very simple in what they're doing, taking an incoming request, putting it on the queue. This is less fast, it's slower, right? And because these requests, depending on what the request is, certainly the simple task of taking a connection and putting that request on the queue is a lot faster than actually performing the work, like getting a file or calculating something. And so, how you deal with this graceful degradation is to say, well, I know that one thread can handle on order of a certain number of requests per second or requests per minute, some unit time. I know the resources I have on my machine, right? Memory and computational, and the number of cores on my processors, and I have so many processors on the server. So I know how many of these workers I'm going to have, right? And so this set of workers is called a thread pool. And in the mid to late 90s, we had to implement this ourselves. They didn't have language support for it, right? And so one of the ideas with the thread pool is, okay, this system degrades more gracefully because rather than saying, okay, I'm going to shut off my service the moment it hits the upper bound of the available resources, now, the burden is either I consume more thread resources, and this is finite, you can only go up so high for an operating system until you exhaust it. But you have a really sophisticated way to say, okay, well, I have this pool of workers, and some worker instances, some threads, might be faster because maybe the request is simpler, and some might be slower. You're also saving on resources, and that's valuable computation, by not having to exit the thread and then recreate the thread, and then exit the thread and recreate the thread. Yes, absolutely, to create a thread is much cheaper computationally than creating a new process. Because as we said, for a process, you have to create a whole new process control block, and then you put it on the ready queue, and then it gets scheduled. A thread only involves a program counter and the register file, right? But what you're saving here with a thread pool is that these threads don't ever exit. They just stay there. And so if there's no work, the thread remains idle and it's in a weighted or blocked state, right? So it doesn't use any CPU resources. And the moment any work occurs, the thread is already there. So you don't pay that small cost computationally to create a brand new thread. You're not calling pthread create. You call create for all the threads ahead of time. And now that computation that would have been used to create the thread and exit the thread and create the thread and exit the thread, you're now using that valuable CPU time to actually do real work, right? And so this idea of this group of quote unquote generic workers is called the thread pool. And how it's implemented is just literally at the beginning of your runtime, you create your threads, and that allows you to scale your load on your machine. But also, from a degradation standpoint, what happens? There's a point where, as the queue grows to a certain length, right, each of these is going to be busy, but it's more likely that one of them is going to get freed up sooner than if you did the pthread create on demand, right? Because you do the pthread create on demand, now some new person comes in, and let's say you hit that limit, all of a sudden you have to say, okay, well, I did pthread create, I can only call it 1,000 times. And let's say it was called 1,000 times, pthread create each time a request came in, and that involved putting the, let's say you had a unique thread as the request came in. Once the thousand and one person comes in, you have to deny that person service, right? Because you've reached your threading limit. In this case, you add it to the queue, and the only consequence is it just takes a little bit longer for that person's request to be processed. You understand the difference? And so in the first case, when we had a server, and I'm going to draw it a little bit smaller, you had the incoming request, and the request came in, and a new thread was created, and that thread was responsible for interacting with retrieving the request, performing the work, and then returning back the response. In this case, you have two groups of threads. One group of threads is only going to add that request to a queue, and another group of threads is going to take the request, do the processing, and return the result directly back to the client. And in this latter case, the reason why it scales better is because the consequence here is that once you hit thread 1000, let's say you can no longer allocate a thread, a new client comes along, say client 2, its request comes in and says, I can't go to 1001. You can't have any service. And to you, the consumer, this looks like you go to netflix.com, you select your video and says, sorry, you have to come back later. Well, I'm paying, each month, I need to, stream my movie. In this case, that doesn't happen. It adds that new request 1001, to the end of the queue, and then eventually one of these is freed up and it picks it up, and you just perceive it as it being a little bit sluggish. Now, certainly, this is not a magic solution, right? Because eventually this load can get so high that it takes too long to eventually get to it for one of these workers. But that's just something you do in test to say, okay, I'm going to partition my workload so that once it has a certain load, I'm no longer going to push requests to that server instance. I'm going to push it to a different server instance. Okay? So this is why thread pools are important. Not only does it give you more graceful degradation, right? It gives you a slowdown instead of just a stop. It also allows you to scale and tune better your computation to the available resources on your machine. Any questions about this? That make sense? Yeah? Okay. So advantages of thread pools. It's a slightly faster to service a request, and as you scale to internet, because you're not recreating each thread and tearing it down each time, that savings is being used to perform more work. So for a single thread, it's only slightly faster, yes, but as you scale your load, that slightly faster for each thread and each request, it adds up to better scalability. So it also allows the number of threads in an application to be bound to the size of the pool. So if you have a thread pool, what that means is that you decide ahead of time how many worker threads you're going to have. So let's say you have a browser or some application, and the application has a bunch of functions it wants to do. So what it does is it says, okay, well, is there an available worker? I'm going to give that function to worker 1. I'm going to give this other function to worker 2. And you keep handing out these functions to these different workers. And you decide ahead of time how many resources, in terms of thread resources, you're going to use at the point where the application starts. So you can do better capacity planning for your hardware. And so it allows the number of threads in the application to be bound to the size of the pool. And also, and this is another important one, you separate the task to be performed from the mechanism that you use to run that task. And so here we have this thread pool, and this thread pool says, well, I know how to run any kind of request. And now you just have a bunch of requests coming in. And so rather than closely tying the unit of work to the type of work being done, you're separating the two, and that allows you to now scale differently the amount of work your system can perform. Okay, and so the other benefit, separating tasks to be performed from mechanics of creating the task, allows different strategies for running the task. So now when you have this thread pool, underneath the covers, if this is my operating system, right? If this is my OS, and let's say I have a bunch of cores, and this is core 1, this is core 2, this is core 3, you can now say, okay, well, this group of workers or threads, I want to put on core 1, the next group I want to put on core 2. So now you can do some very sophisticated partitioning of your data set and parallelization and workload balancing that you couldn't do otherwise. And so from the perspective of the system design, right, these clients don't care how the work gets done. So you can have the work layout done all sorts of different ways because you've abstracted that with that thread pool. How you choose to lay out the workers on the cores or map them onto cores in the thread pool is completely up to the thread pool. That's disjoint from the type of work that needs to be done, right? You could even say, all right, well, this thread pool, if the work involves a certain type of matrix operations, this core has attached to it a high-speed channel to a GPU, so it's going to go to this core, right? So now you can start to make use and exploit parts of the hardware that you otherwise couldn't, but that is separate from the type of work. And that's kind of nice programmatically to not have to worry. So you could effectively, in an engineering team, you could have one group manage these decisions, right, about how they map to the underlying hardware. And then you can have another group make these decisions about what type of work to do. Okay? All right. Any questions about this? Does that make sense? Let me do a time check. 17. All right. Thank you. All right. I need to make sure I finish in about 15 minutes. There are Windows APIs to do this. Windows isn't the only platform that does this, but certainly Windows has it. And this is in Java. The thread pool APIs, there are different types of thread pools. There's a single thread executor, and these are static methods on the thread pool class. And I encourage you to Google search it. There's doc on it all over the place. And so single thread is just a pool with one thread worker. A fixed thread pool has a certain pre-allocated size. And so when you call this factory method, as it's called, it creates the thread pool, and size is the number of workers in the pool. And then a cached thread pool is one that is unbounded, right? So it keeps creating more and more and more threads. But the benefit with this cached one is once, let's say, your requests, let's say you have 10 requests, then if you only have one request, you're going to get one thread. The second request comes along, and you get two threads. The third request, four threads, three threads, and then four threads. And let's say you have 10 requests waiting, right? You're going to have 10 threads, and the number of threads that you instantiate in the pool, it does it dynamically, and it grows the size of the pool to match the amount of workload that you have waiting in the queue. Now, of course, let's say after you have 10 requests in the queue, your workload is 10 units of work. Let's say that shrinks down to 3. The thread pool remains at 10. And those threads that are extra, they're sitting idle and they're reused still. So what this cached one does is it grows the size of the thread pool to meet the size of the workload. And then as your workload increases, eventually it increases the thread pool. Okay, but these threads are reused. You can have thread pools that also shrink, but that's beyond the topic of this discussion. You could spend a whole career dealing in high performance server design and looking at the choices about the thread pools and the mapping to the underlying architecture and all sorts of stuff like that. Okay, any questions about this? Does it make sense? Okay, so this is a very simple example of a cached thread pool. And it's in Java. Um, it's a lot of moving parts to do thread pools in C. They do exist, but we're just going to look at the Java one because that's what's in the book. And so you call this factory method, which is a static method on this executors class. So you call new cache thread pool, and you get this executor service, as it's called. It does and manages the execution for you, right? So now, anytime you want to add a new task, right, you instantiate that task, and that task is specified in the constructor on the execute method. And so you add it to the pool, and the pool just handles everything else for you, right? And I would refer to the Java doc for details. This is just to give you the high level idea of what a thread pool is and why they're important. And then after that, you shut down the pool, and that handles the graceful teardown of all those thread resources. So you can do all those thread exits and reclaim those resources. Okay, so let's take a look at some issues. Well, threading is beneficial, and thread pools are very beneficial. We talked about scaling and stuff like that. But of course, with every new and helpful tool, there are practical issues in place, and that's the cost you pay. So one of the things and decisions that are made, and this is kind of a sticking point, is what happens when you call fork, right? Fork says, I'm going to replicate the process, but let's say a thread, and you might have some number of threads in a process. One of them calls fork. What do you do? Do you replicate the entire process, meaning all of the threads, or do you replicate just one of the threads in the new process? A decision has to be made. And so, signal handling. Signals are a way of the operating system communicating that something went wrong, and it communicates that to the program. So, if some thread does something, or let's say something happens to the system, and the operating system is notifying, for example, somebody has called shutdown on the operating system. So the operating system goes to each process and says, shutdown signal, shutdown signal. It's notifying everyone that you need to clean up, and because I'm getting ready to exit. So if you have a signal, who gets the signal? Do all the threads get the signal from the operating system, or do some of the threads? Is it just the thread that had made some offending call that gets the signal, or does everyone? Then there's also the cancellation of a thread. So you can call cancel and prematurely kill off a thread before that thread has exited, right? That's very, very tricky to manage. There's also thread local storage, right? Thread local storage is, as the name implies, it's memory that is specific to that one thread, and it kind of looks like static variables. Uh, as every function that the thread calls, it can see that memory, but no other thread can see it. It's almost like privately allocating some piece of RAM, right? It's called thread local storage. Then there's also what's called schedule activations. That's something called lightweight processes, and it's a mechanism for managing the relationship between kernel threads and user level threads. Okay, so fork. Some of the questions: do you duplicate all the threads or some of the threads? And if you look at different Unix distributions, you'll see that they have different philosophies on that. Some offer two different ways of doing forking: the forking that only replicates the calling thread, right? So you have a single threaded new process, which is a copy, but you only have that thread that called fork is the only one that exists. Or do you replicate all of the threads, right, in the copy? So that's a decision you have to make. So exec works as normal when a thread calls exec after fork. Of course, that loads the new program, and when you load the new program, now you're dealing with that new program in its initial state with that single thread. Okay, but this fork, it's a real issue. You have to think about that. And so, if you're designing a system, and you have to choose your operating system wisely, in particular if you're dealing with high performance server applications, right? Because making the wrong choice for fork, if that facility is not available, can really dramatically affect your performance as well as the resources that you have available. Okay, signals. And so a signal is associated with the operating system, and the operating system takes a default action associated with each type of signal. And a program can override this signal handler, and that handler is the action that's taken in response to the signal. And so when you have a signal, who gets it if you have multiple threads? Does a single thread get it? Do all the threads get it? What's going to happen there? Now, that just means if designing high performance applications like databases and servers and streaming servers and stuff like that, you have to make the choice of your operating system wisely, the one that's going to sit on each node or each machine or server instance in your data center. Okay, so is it generated by a particular event? Is it delivered to a process? Is it handled only by one handler? Or is it every thread? Okay, so those are choices you have to think about when you're dealing with a lot of this stuff. And so every signal, I said that before, has a default handler, but you can override it. And so if you have a single threaded application that's delivered to the process, but for multiple threads, you have to decide what's going to happen, who's going to get this signal, and what are they going to do with it. Okay, so more signal handling. Where should it be delivered? I just talked about that. You can deliver it to all threads, to one thread, to some threads, or you can just have a thread that's the one that always handles the signals, takes some action. It's really up to you, right? But you have to define that. And each choice you make has a consequence on your performance as well as the state of your process and its ability to gracefully handle or react to these signals that can occur. Okay. Any questions about this? Make sense? Okay. And so let's take a look at thread cancellation. Thread cancellation is the termination of a thread before it's ready to terminate, right? And so when you do thread cancellation, the target thread is that thread which is the so-called victim, the one that will be terminated before it's ready to. There's two types of cancellation. There's asynchronous cancellation. That means the thread that is canceled, the target, terminates immediately. And then there's deferred cancellation. In the deferred cancellation case, you're kind of making a note and you're waiting to cancel only when you're ready to check a certain function, right? And this function checks for cancellations that are incoming, cancellation requests. And so how it looks with this deferred cancellation, periodically a thread in the code might call check for cancellations. And if there's a pending cancellation, it goes ahead and gets canceled. Okay. So why someone would use this deferred cancellation is that if you just immediately terminate a thread, you don't give it an opportunity to clean up resources that it might have been consuming, right? But with this deferred cancellation, you can periodically through your thread implementation say, okay, perform some operation, clean up, check to see if there's a cancellation. Perform the next operation, clean up, check for cancellation. And so in that regard, you give it an opportunity to gracefully clean up because you don't want to leave memory resources and things like that open. Okay. All right. So this is not terribly important, but I will comment is that the thread can be in a certain state, and when a cancellation comes, it could either ignore that cancellation, it can perform that cancellation, whether it's deferred or asynchronous. And so this thread can decide to disable this whether or not it pays attention to these cancellations. And so the thing to pay attention to here is the type here and the state. And so if this cancellation mode is off, it ignores it. If this mode is set to deferred and it has been enabled in the thread itself of interest, then it'll go ahead and do the deferred cancellation. If it's asynchronous and it's enabled, it'll go ahead and it'll terminate immediately. And so that function, pthread test cancel, is what your thread would call after doing something, cleaning up a resource, then it calls this pthread test cancel. And if there's a pending cancellation for the deferred cancellation, it'll go ahead and do that cancel, right? So if you're going to have thread cancellation, let's say you have a thread pool type implementation like this, and you want to be able to say, okay, well, if my resource consumption on my system gets too high, I'm going to start canceling threads. Now, if a thread is in the middle of handling an interaction with a client on the other end of the internet, and maybe after sending that response back, you need to go and free memory or free some shared memory or unattached shared memory that it has allocated, you want to do that test cancel approach, that deferred cancellation, because you want to give it an opportunity to detach and free up the shared memory if it was using shared memory. If you don't, what'll happen, it'll exit, not get a chance if it's asynchronous, not get a chance to free up the shared memory. And then as you keep using up shared memory but not freeing it, eventually you're going to run out of memory, right? And that'll just bring down your whole server. Okay. All right. Any questions about this? Make sense? Okay. So thread local storage, lastly, it allows each thread to have its own copy of data. You don't have control. It's useful when you don't have control over the creation process, kind of like what happens with thread pools. And so each one can kind of have its own little memory bank, if you will, that it can use to store stuff and manipulate things. And that's really important in some applications. Okay. So lightweight processes, lastly, is a construct that's used to manage the relationship between kernel threads and user level threads. I know Solaris had it from Sun Microsystems and Oracle bought Sun Microsystems. I can't think of another operating system that uses lightweight processes. I'd have to go back to documentation and see. But lightweight processes is typically something for high performance applications, right? You can associate these lightweight processes with specific processes called giving it a processor affinity. So you can say, all right, prefer to run on these cores and not those cores. So you can very specifically partition your workload. And this is useful for M to M, many to many type threading models. We have some number of kernel threads responsible for some number of user level threads. And typically in practice, you're going to have fewer kernel threads mapped to a larger number of user threads. And so what this lightweight process does, you can think of it as the binding between the two, and you make what's called an up call, right? And so this kernel says, okay, this kernel thread says, okay, I want to associate with a user thread. So I'm going to call up between kernel and user space, and that's going to invoke some function in the user level thread. Okay, and so this lightweight process is a software construct, and it's used as an intermediate data structure, kind of like the API, if you will, between kernel threads and user threads. And it looks like it's a processor, right, on the system, right? Because if you think about it, it can perform computation, but it has these units of computation, these instruction streams, as seen by the CPU or cores, which are the kernel threads. And so each lightweight process is attached to a kernel thread and could be multiple kernel threads. And so now when you're trying to scale your system, the question is how many lightweight processes should you create? And then you start assigning them to different cores so that you can efficiently use your resources. Okay. And so what happens is the scheduler provides what are called up calls. So it says, okay, what do you want to do next? So you call up, if you will, from kernel thread into the user level thread in order to instantiate this mapping. Okay. All right. Any questions about this? And so this really comes into play when you're doing high performance applications because the name of the game is trying to squeeze out every last MIP of computation, millions of instructions per second, or MIP is the unit of CPU strength, if you will. And so you want to squeeze out every last MIP that you can from your architecture and leave no part idle, right? And so you're going to create lightweight processes, you're going to create threads, you're going to assign them to each core. You're going to take advantage of any specialized hardware if you have GPU resources or custom ASICs to do calculations and things like that, right? And this really comes into play if you're going to design high performance servers. And of course, high performance matters for things like streaming, scalability for web servers, all sorts of stuff. Google Maps to do Street View, you need some pretty high performance servers to stitch together these images and give you the illusion that you're really driving through. Those are separate images that are being pasted together and rendered by your browser for you. Okay? All right. Any questions about this? Make sense? Okay. So I think, examples. Okay. I forgot about this part. Okay. So we have some examples, and this refers to the underlying implementation of how you actually create threads and create processes. Underneath the covers in the Linux source code, they call it cloning. And they make no distinction between a process and a thread. The only difference is what things that you have the clone reproduce, right? And so this clone says when I create another copy of a task, I can either create the same memory space, right? Share the same memory space, or each one gets a different memory space. When you're forking a process, if you recall what that does, you have a whole new copy. Each one has its own memory space. When you're creating a thread, you have the same memory space, but you're just creating a different execution context, which is a program counter and a copy of the register file. And so this clone is a single routine, if you will, within the Linux source code that is the common place where you're going to replicate units of execution. And so when you call it a thread, you're keeping the same file system information, you're keeping the same memory space, and sharing the signal handlers, and you can control finally what aspects of this replicate are shared or if they're going to be unique. And so whether it's a thread or a process, the same cloning routine is used. Okay. Any questions about this? I have to check the time. 10:34? Okay, thank you. So that's the end of our module on threading. And I will pick back up on today's Thursday, Tuesday, with the next part of the module. And I'll think about the design of the final project and think about assignments along the way to contribute to that. So please make sure you're keeping up with the reading. I will see you all on Tuesday.